For the rest of the section, it's going to be the calculus of parametric equations, in which we are going to find derivatives, first and second derivative of a parametric equation, and then some applications using integration to find the arc length in parametric form. All right? So, well, so we have a couple of equations in parametric form, an equation in terms of an equation for x in terms of t, and an equation for y also in terms of t. So they both have to be differentiable for certain interval that we want to do this process. And well, the way to find the derivative in parametric form is by dividing, actually setting dy dt, supposed to highlight, dy dt over dx dt, which is basically the derivatives of the x equation with respect to t and the derivatives of the y equation with respect to t. All right? And well, other pieces of information is that we've set the denominator equal to 0 to find the values where we have vertical tangencies, and the numerator equal to 0 when we have horizontal tangents. It's basically the same information, the same from Calc 1, right? When we do the first derivative test. For the second derivative, it's a little bit tricky, so we take the second derivative of the first derivative with respect to t, and we divide that by the same derivative with respect the same first derivative with respect to of the first equation. Well, how about we look at one example so we can see this in action. So we have this curve represented by the equations x equals t squared, y equals 3t minus 5. They're asking us to find the slope of the curve at, well, number 1, time t equals to 2, and, well, in this case for part B is the point where the particle is at 9.5. But first, in this case, we need to figure out what that time is. Well, let's do time t equals to 2. So number 1, let's write down the equations. So we have, let me rewrite the parametric equations. That's x equals to t squared and y equals 3t minus 5. So let's take the derivatives with respect to t. That is dx dt and dy dt. Or if you want to use the other notation, the more compact notation, that will be x prime and y prime. But I would like to use Leibniz notation because that's the notation we have in the definition box. Well, let's just use the same differentiation rules as usual. The derivative of t squared with respect to t is 2t, and the derivative of 3t minus 5 with respect to t is 3. All right? Setting up the derivative, dy dx is going to be dy dt, that is the derivative of the y equation over the derivative of the x equation. And for the derivative of the y equation, we got a 3. And for the derivative of the x equation, we got a 2t. All right? Yes?
Does the order matter? Because right here I said dy over dx.
So dy dx, and yeah, I have dy dx here, and dy over dt, dy dx. And so that's the first derivative with respect to t. Well, it's a function, even though it's dy dx, but because these y and x's are described in terms of t, well, this is going to be a function of t. So we're going to use this to evaluate the derivative dy dx at t equals to 2. So all we have to do is substitute the number 2 wherever we see the letter t. And well, let's simplify this. That's 3 over 2 times 2, which is 4. That's 3/4. All right? So, well, what happens for letter B? So for letter B, we don't know what's the time where, or what's the value of t for which the particle is at the point 9, 4. So we need to figure that out first. Number one in this case, well, because we're looking for a position, we will need to go back to the original parametric equations, not the derivative. Recall that in this case, the derivative of these parametric equations are basically going to give us the piece of information for the velocity, all right, or speed, depending on the context, right? But well, we need to find the time where the position is 9, 4. So let's go back to the original parametric equations. X equals to t squared, y equals to 3t minus 5. All right. Okay, so what we're going to do is set x equals to 9 and set y equals to 4. Plug them in the corresponding left-hand side of each parametric equation. That is, oops, that's 9 equals t squared and 4 equals 3t minus 5. Alright, so we need to solve the equation for t, but notice in this case we have two options. Well, one way to go about this, and that's one way that I've heard of, it's to just solve the easiest equation that you see in the system. And by easiest equation, I think it's the second one, because it's a linear equation. You would get only a single value. However, the other way I learned this is actually we have to solve both equations and go with the value of t that actually repeats. For example, let's see. I think it's a little bit big. Oh, never mind. Okay. So I'm going to solve t squared equals to 9 and 3t minus 5 equals to 4. Well, t equals plus or minus 3. That's the square root of 9, plus or minus. And then 3t equals 4 plus 5, that's 9. And t equals 3. So in this case, which one are we going to get? So from here, notice we get t1 equals to negative 3 and t2 equals to positive 3. We are going to go with the one that repeats. The positive one, exactly. And let me write it down as a side note. Go with the one that repeats. In this case, the positive 3. And that's the time at which the particle is at the point 9, 4 when it follows the path described by that set of parametric equations. So we may now find the derivative at that value of t. So that is dy dx evaluated at t equals, in this case, 3. Well, that's going to be 3 over 2 times 3. Cancel the 3's, that's a 1/2. Alright? Well, yes, it's a lot of calculation, crunching numbers and symbols, but I mean, what's the meaning of what we have just done? Well, we're finding consider this as a particle in motion along in the x and y direction. The first derivative is giving us the velocity, that is, it's traveling at this with a velocity of 3/4 to a velocity of 1/2, or that's the steepness of the path also that it's traveling to. Alright, so let's look at letter C to find the second derivative in parametric form. So for the second derivative, the formula is a little bit more complex. Okay, let me write it down. That's the derivative with respect to t of the first derivative that we already found out, of the dy dx that we found in part A. And then divide the whole thing by the derivative of the x equation with respect to t. And well, so what's that result? Let me highlight so you can see where is this coming from. So this dy dx right here is the same as this quantity right there. All right. And well, I'm going to continue over here. So the derivative with respect t of the quantity 3 over 2t divided by the derivative of the x equation that we got it from here. This one we got it from this one, which is this 2t. All right. So this is 2t. Oh, come on. It's the highlighter. That's 2t. And well, we cannot differentiate this 3 over 2t because the t is in the denominator of that fraction. Let's write it down to the numerator. 3/2 t to the negative 1 over 2t. And that's negative 3/2 t to the negative 2, the whole thing over 2t. And this will be, okay, number 1, negative 3/2 divided by 2 is the same as having negative 3/2 times 1/2. That's going to be negative 3/4. And well, this t to the negative 2 power, I'm going to send it to the denominator with positive exponent times that t. And let's just multiply those t's in the denominator. So that's going to be negative 3 over 4t cubed. And that's the second derivative. All right. Let's look at another example, one that involves trigonometric functions. They're only asking us to find the first and second derivative, not to compute anything like slopes or anything, just to. So in this case, well, we have the x equations and the y equation. Let's find the corresponding derivatives. dx dt and dy dt. Well, the derivative of sine squared. Be careful. How do we find the derivative of the sine squared? Which differentiation method? Chain rule. All right. So chain rule. This is basically the same as saying sine t to the second power, and yes, that's going to be a mini chain rule. So 2 sine t minus 1 times the derivative of sine, which is cosine, and the derivative of sine, which is negative sine. Okay, let's set up the derivative dy dx, which is the quotient between the derivative of the y equation with respect to t and the derivative of the x equation with respect to t. So the derivative of the y equation is negative sine, and the derivative of the x equation is 2 sine t cosine t. Alright? And notice how these signs cancel, and we get negative 1 over 2 cosine. And we can further use trigonometric identities. We can write that cosine to the numerator using which function? Secant. Okay, so we can use that as a secant. So negative 1/2 secant. So that's our first derivative here. All right. So again, we're going to use exactly the same differentiation rules for the individual differentiation of the x equation, the y equation. What changes here is how we put together for the derivatives in parametric form. So now for the second derivative, dy d squared y dx squared, that is the derivative with respect t of the first derivative that we obtained in the previous part, and that whole thing divided by the derivative of the x equation, the same one we obtained in the first part. Okay, so again, let's color code this. So this is this quantity right here. It's going to go here. So that's going to be the derivative of negative 1/2 secant t over the derivative of the x equation, which is 2 sine t cosine t. So what's the derivative of secant? Secant tangent, but in this case we have that negative 1/2. This will be negative 1/2 secant tangent over 2 sine cosine. And well, yeah, this is basically the derivative. I mean, however, if you're given something like this on the homework, and if you put that as a final answer, it's gonna tell you that although your answer is correct, it's not written in the most simplified version. So in this case, let's use trigonometric functions or trigonometric identities to rewrite this. Okay. In particular, let's use secant as cosine in the denominator, and let's use tangent as sine in the numerator and cosine in the denominator. All right, so and I'm going to write this negative 1/2 with a 2 in the denominator instead of having this complex looking fraction, but I'm going to keep this negative sign. Don't forget that part. Okay, so that's going to be secant goes down to the denominator as a cosine. All right, cosine t, it's this one, and then sine t, cosine t, and then this tangent right here will leave a sine in the numerator and another cosine in the denominator. Let me color code this just so you can see where are these coming from. So again, this secant right here is becoming this cosine in the denominator. All good? And on the other hand, this tangent is becoming the quotient, this quotient sine over cos. All good? Well, the rest of the problem is just divide out any common factors, in particular these two sines, and we will be left with how many cosines? All right. However, I mean, yes, should be over 4. That is true. Thank you. That's what I would like. Wait a minute. Something's going on that it's not going on here. All right, that's 4. And that's negative 1/4 cosine cubed. Or if you prefer, either way. Either way is fine. All right. Questions about this one? Let me also color code this one right here. All right. For example, number 14, find the slope, the equation of the tangent line, and describe the concavity for the curve given by, well, x equals t squared minus t, y equals t cubed. So, yeah, concavity, that's the second derivative test. So we're going to take some derivatives, set some equations. Well, all right, okay, yeah, this one is going to take a good minute to go. Well, let's find the derivatives first. Why not? Let's start with the first things first. dx dt and dy dt. The derivatives, well, just general power rule. That's 2t minus 1 and 3t squared. This means that the derivative. Oh, by the way, something I didn't write here. I didn't type on the exercise. At t equals to 2. I mean, we're going to find an equation, but where? We're going to see the concavity, but where? right? So I didn't type that part. All right, so number 1. Let's find the slope. Okay, they're asking us for, well, we actually need the slope because they're asking us to find the equation of the tangent line. So we need to find the derivative dy dt, dy dx, which is the quotient between dy dt over dx dt, and well, the derivative of the y equation, which is 3t squared, and the derivative of the x equation, which is 2t minus 1. All right, and well, because we need to find the value of the slope at that particular time, well, so we're going to plug in t equals to 2 in this derivative right here. So the derivative dy dx at t equals to 2, it's going to be, well, replace t, whatever you see the letter t, replace it with a 2. And well, that's a 4 times 3, that's a 12 over 2 times 2, which is 4 minus 1 equals 3, and reduces to 4. So that's the slope. All right. Now there's another piece of information that we need to, in order to find the equation of a tangent line. So number 1, we have the slope, possibly the hardest part because, well, that requires finding the derivative in order to find the slope. What's the other piece of information needed to find a point? Well, how do we find that point? Well, point again is position, and that position function, which one is it? Is it the original set of parametric equations or the derivative? Which one is it? The original, right? So we are going to plug in x of 2 and y of 2. That's 2 squared minus 2 and 2 cubed. So 2 squared, which is 4 minus 2, that's a 2, and 2 cubed, which is 8. So the point will be 2, 8. So we have the two elements that are required to find the equation of the line. Well, we have a point, we have the slope. Let's use the point slope form. Y minus y1 equals m times x minus x1. And from here, well, you know the drill for this one, I guess. So that's a y minus 8 equals 4 times x minus 2. Y minus 8 equals 4x minus 8. And you can just cancel the x, y equals to 4x. All right. Let's see. So what we have already, the slope, the equation, and now let's describe the concavity. Again, concavity, that's a piece of information that we obtained from the second derivative of a function. So we have to go ahead and take the second derivative, d squared y over dx squared. That's the derivative with respect t of the first derivative that we already took in the previous part, and divide by the derivative of the x equation. Okay, and again, let me color code this so you can see where is all this coming from and how we're going to connect everything. So this is the derivative dy dx, which is this quotient right here. That's going to go here, right? So that's the derivative with respect t of the quotient 3t squared over 2t minus 1. And yes, I know, this one is going to require the quotient rule. 2t minus 1. Alright? And well, let's recall what the quotient rule for differentiation is, of course. So recall that when you have a function of the form uv, its derivative is u prime v minus v prime u, the whole thing over the v squared, that is the denominator squared. Which is what we're going to apply to differentiate that 3t squared over 2t minus 1. Alright, let's go ahead and find that derivative and simplify it as much as possible in this case. So the derivative of the numerator, which is, okay, that's 6t times the denominator 2t minus 1 minus the derivative of 2t minus 1, which is 2, times 3t squared. The whole thing divided by these 2t minus 1 quantity squared. Alright? But be careful here, because that's only the derivative of the numerator, the quantity in the numerator. This whole thing, it's still being divided by these 2t minus 1 in the denominator, right? Let's do something to clean that up. So what I'm going to do here is, so this whole thing being divided by 2t minus 1 is the same as multiplying by 1 over 2t minus 1. So basically these two multiply, and this is, the denominator becomes 2t minus 1 quantity cubed. Are you following me here? Yep. And well, let's simplify the numerator, this funky looking numerator. So distribute, and these two just multiply 2 times 3. There's really nothing really crazy. Okay, so 6t times 2t, that's 6 times 2, that's 12t squared. And 6t times negative 1, that's minus 6t. And minus 2 times 3, which is 6t squared. Oh, some terms are going to get cancelled because these are like terms. So 12t squared minus 6t squared, that's going to be 6t squared minus 6t, whole thing over 2t minus 1 quantity cubed. So that's the second derivative, alright? But well, in this case, no, we're not going to set anything equal to 0, because they're not asking us for the intervals in which the given function is concave up or concave down, and therefore finding point of inflection. No, that's not the question. They're only asking us for the concavity at a given point, which is better, because all we have to do here is simply evaluate the second derivative at t equals to 2. And well, okay, let's find the value first. So that's 6 times 2 squared minus 6 times 2 over 2 times 2 minus 1 quantity cubed. Well, that's going to be, okay, 6, okay, 2 times 2, that's 4 times 6, that's 24 minus 12, is that a 12? And 2 times 2 is 4 minus 1 is 3, 3 squared is 27. Well, doesn't matter. It doesn't matter what the value is. Well, let's actually simplify. That reduces to 4 over 9. But doesn't matter either, because in order to judge the value, or I mean to describe the concavity by the value of the second derivative, well, in this case, this is a positive value. This is greater than 0. What is that going to tell us? Concave up or concave down? Concave up, right? Concave up. Alright? So that's the only question. What is the concavity at that point? Not finding the interval. So if that were the question, then we would have to go by setting the equations equal to 0, which is great. Alright? Let's do one more. Yes, we have time for the next topic. Let's see. So we did some differential calculus in the parametric world, in the parametric setting. Let's do some integral calculus, and in this case, the only thing we cover is arc length. And well, look at the formula for arc length. Is very similar to the one that we learned at the beginning of the semester. I mean, even the derivation for this is a lot simpler than the one that we did in at the beginning of the semester. I mean, because it's only, you have a path like this with x, y at different values of t, so you want to find the distance, so this is like a triangle. That's basically the change in x with respect t, and this vertical change is is dy dt. Pythagorean theorem, square, take the square root and add infinitely many of those lengths. That's the integral, right? I think it's easier to describe it in parametric form this time. So let's go ahead and do one example. And well, let's find the length of the curve given by x equals t squared plus 1 and y equals 4t cubed plus 3 over the interval -1 to 0. And these exercises are going to be worded in a very straightforward way. You will be given an x equation, you will be given a y equation, and you will be given an interval over where to integrate to. So all we do is, number one, let's find the derivatives, dx dt, dy dt. And well, that's 2t, and that's 3 times 4, that's 12t squared. Just differentiate basic polynomials. There's nothing weird. Okay, so L, which is the integral from -1 to 0 of the square root of the dx dt quantity squared plus the dy dt quantity squared. Well, in this case, that's the integral from -1 to 0, and that's the 2t. Be careful when squaring the 2t and the 12t squared, because this square is going to affect not only the variable but also the coefficient. That's a very common mistake, to just write this, oh, that's 2t squared and that's 12t to the 4th power. No, we have to square both the coefficients and the and the variable. So that's 4t squared plus 144t to the 4th. Okay. Looking at this integral, if we start thinking of a good strategy to evaluate that integral, well, U-substitution is definitely not going to work, because look at what we have inside of the radical. It's a degree 4. So we wish we had something 1 degree less multiplying with the dt, but we don't have anything. However, we can actually simplify the integrand. In fact, notice there are GCFs and there are perfect squares that we can very easily factor out. So that's the square root. Okay, so it looks like a t squared is a GCF, and for the coefficients 4, it's also a good GCF. And that's going to leave us with 4 times what number equals 144, I believe it's 36. 1 plus 36, t squared. Well, from here, the radical of a product is the same as the product of the radicals. And simplify the one that we can simplify. In this case, the first one, the square root of 4t squared. What's the square root of 4t squared? 2t. Be careful. Recall that when we're taking the square root of something squared, when we have a variable, that's the absolute value. because that can be either positive or negative, and be careful on this one because notice also the interval that we're integrating at. So we're integrating over a negative set of numbers from -1 to 0. So in this case, number 1, that's the integral from -1 to 0 of absolute value of 2t. All right, and 1 plus 36 t squared dt. And yes, in this case, whenever you define this absolute value 2t, you can either have the negative 2t or the positive 2t, and that's going to depend on whether t is positive or negative. And in this case, if you observe the integral, the limits of integration, they are in the negative side. So that absolute value of 2t will be negative 2t integral of 1 plus 36 t squared. Okay? From -1 to 0. And well, let's take out the 2. How about that? Outside of the integral. And I think we can do the U-substitution in this case. So u equals 1 plus 36. And that's what we have now. 1 degree less multiplying the dt, which will stand the du part of the problem. So u equals 1 plus 36 t squared. du equals 72t dt. And t dt, 1 over 72 du. And well, you might want to also change the limits of integration, u of 0 and u of 1, that to simplify calculations. That's 1 plus 36, and technically that's the correct thing to do. 1 plus, so that's going to be 1, and 1 plus 36 times -1 squared, 37. All right, I believe that's what I did here. Yeah. And I know this one is going to look a little crazy. You'll see why. So that's the integral from 37 to 1. Oh, that's a -2 over 72. And that's the square root of u du. -2 over 72, 1 over 36. Well, I'm going to change the minus to a plus. How about that? We can do that by reversing the limit, and I think when we do that, it makes more sense to have a smaller lower limit and a larger larger upper limit, isn't it? So this property, okay, let me list it here. Let me list that property just to make sense out of it. When you have the integral from a to b, f of x dx, this is the same as integrating from b to a instead, the same function, as long as you use a minus sign. Yes?
Where did you get the negative from in front of 2?
The negative, because in this case, this absolute value of 2t will be -2t whenever t is less than 0 and 2t is greater than or equal to 0. But in this case, since we are integrating over a negative set of numbers from -1 to 0, then we have to use the negative counterpart. All right? So that's the integral property. I think that makes the problem more friendly to look at. All right? And well, so that's u to the 1/2 du, and that's 1 over 36 u to the 3/2 over 3/2 from 1 to 37. And well, 1 over 36 divided by 3/2 is the same as being multiplied by 2 over or 2 over 3. So that's going to be, okay, this one, 1 over 36 times 2 over 3. So that's half of 36 is 18. 18 times 3 is 54. All right. So 1 over 54 u to the 3 halves from 1 to 37. And well, you might remember this type of calculation from arc length back in at the beginning of the semester. These weird looking numbers. That's 1 over 54, 37 to the 3 halves minus 1 to the 3 halves. And you might remember that we rewrote this. Okay, let me do it on the side because I'm kind of running out of space. This 37 to the 3 halves back at the beginning of the semester, we wrote it as the square root of 37 square root of 37 cubed, which is the square root of 37 squared times the square root times 37. And then we use properties of radicals to get 37 root of 37. All right? That's what we did before. Okay, let me erase it. And that's 1 over 54 times 37 root of 37 minus 1. Final answer. All right. For the next one, yes, we have time. It's not that long. Okay, so let's derive the formula for the circumference of a circle with radius a by finding the arc length. Well, number one, what's the formula for the circumference?
Pi times the diameter.
Pi times the diameter, yes. So on the one hand, the area, circumference, pi times the diameter, but instead of diameter we want radius. That's 2 times the radius, so 2 pi the radius, but in this case they're telling us that the radius is labeled with a letter a. So this is what we want to obtain, 2 pi a. Alright? Well, let me rewrite that. A looks a lot more like a 9. Alright. So let's do that by integrating in parametric form. So we need to find the derivative. They're giving us the limits of integrations. There's really nothing tricky about it. No hidden information. So the derivative, I'm going to call it x prime for shorter notation, and y prime. So that's a negative a sine theta and a cosine theta. So those are the two derivatives of each parametric equation, of each component of the set of parametric equations. The arc length will be L equals the integral from 0 to, or rather from a to b first, the x prime squared plus the y prime squared with respect, well, in this case originally with respect to t, but in this case, well, we have theta, it doesn't matter, just change the variable. The integral from 0 to 2 pi, that's the square root of the square of the x equation, that's a negative a sine theta squared plus a cosine theta squared with respect to theta. Well, let's square this. That's going to become positive. That's a squared sine squared plus a squared cosine squared. And well, I think we can see the identity that we can use. We have a sine squared. Oh, I forgot the theta. But in this case, we have that a squared multiplying it. So what we're going to do in this case is 0 to 2 pi. That's the square root of a squared sine squared plus cosine squared. But what is that quantity inside of parentheses equal to? 1. that equals to 1, and that's going to simplify the integral a lot. 0 to 2 pi, that's the square root of a squared d theta. And in this case, well, as opposed to the previous example for which we use the absolute value, well, in this case, this is just a number, and also we are dealing with a geometry context situation for which the radius is always supposed to be positive, so no need to have those absolute values as before. So that's the integral from 0 to 2 pi of a d theta, which equals a times the integral 0 to 2 pi by taking the constant outside of the integral. What's the integral of d theta? Theta. And well, so a times 2 pi minus 0, a times 2 pi, which is 2 pi a. Isn't it what we were expecting to obtain?